Hello and welcome to this session about the dimensioning of a plant with cost-optimized production logic. I am Daniel Caduff and I'm responsible for factory planning at Helbling. After a short overview about Helbling and the project, I will show you how we approach this simulation task. Then I will share with you some challenges we have faced and go into detail on two of them, and also bring you on a debugging journey. Finally, I will share with you my top 4 lessons learned. For the ones of you who do not know Helbling, we are an engineering and consulting company with 4 divisions that cover the whole range from product development and business consulting to construction and IT solutions. What makes us unique is that we can use the synergies from these 4 divisions to set up interdisciplinary project teams to optimally support our customers. A perfect example of the use of these synergies are our factory planning and production optimization services. Depending on the scope of the project, various disciplines are combined in a team, like production engineering, architects, energy, and IT specialists. A team that can be flexibly adapted during the project phases, like strategies, feasibility studies, or the supervision of construction works. Factory planning is one of the areas where we use plant simulation. This can be for entire plants as well as for individual production lines or cells. But we also use plant simulation for the development of complex production machinery by simulating the material flow inside the machines. Since confidentiality is a key element of our business, today, in agreement with our customer, I will only focus on technical aspects. Now I will give you some background about the project. We have been asked by a client to design a greenfield production plant with the lowest possible operating costs, which shall be achieved with a high level of automation and process integration. In the scope of a feasibility study, we first developed the technical concept, followed by a simulation and various cost and profitability calculations. What was the motivation to make a simulation? Beside the proof of concept, the main purpose of the simulation was to support the dimensioning of the production and interlogistics equipment, to really minimize the costs and gather experience on the system behavior for the further development of the plant. What are the main characteristics of the production? The main thing to know about the products is that there is a high variety of articles with different parameters. About the processes, the main thing to know is that they can all have several machines and that they have different process parameters and characteristics like the automation solution. Now, what are the objectives of the cost-optimized production logic? On one side, we wanted to maximize the machine utilization to minimize the costs. A key question we asked ourselves was, which production orders enable continuous operation without waiting times? On the other side, we wanted to optimize the machine allocation to minimize the lead time. And here a key question was, what is the ideal line configuration for each production order? So to summarize, we were looking for the logic with the best compromise between these two objectives. And I will come back to this later. Now I'm going to show you how we approached the simulation task. We approach all our simulations with these 3 generic steps: analysis and program architecture, programming and validation, and experiments. And on this last step, I would like to focus a bit more. For this project, the basic questions to be answered by the experiments were the dimensioning of the production equipment and the interlogistic systems. However, because of the complexity of the system, we ended up in this last step with many additional open points, because we needed to test and understand the behavior of certain decisions in a running model first. Kind of a chicken and egg problem. So how to tackle all these points in an efficient way to avoid too many iterations? We decided to divide the open points in 4 stages that build up on each other. The experiments carried out in each stage were based on a reference model that was iteratively adapted with the findings from the previous stage. We first tackled all the fundamentals that influence all other experiments. with the refined reference model, we evaluated what is the minimum quantity of machines required to reach the target capacity. On that basis, we performed various sensitivity analyses to define reasonable reserves. And with the final model, we evaluated the requirements for the intralogistics like the buffer and transport systems. Now I'd like to focus a bit more on the first stage where we tested different logics. For that, I'm coming back to this chart that I introduced before. As I said, we wanted to find the best compromise between reduced costs and lead time. To understand this chart a bit better, I'm showing what the two extreme cases mean. The extreme on the left would be to always use only one machine per production order. And the other extreme would be to use all machines for only one production order. And we developed four logics that are somewhere in between these two extreme cases. So how did we compare these four logics? From the simulation runs, we exported data about the total changeover time, the buffer sizes, and the lead time. Then we applied some unit costs for the buffer, cost of capital, and the changeovers, and compared how these four logics performed. So the columns represent the costs and the blue line is the lead time. Together with our customer, we agreed to use logic B, which seemed to be the best compromise. Now let's talk about some technical challenges. This is an overview of the main technical challenges that we faced. To iteratively test different parameters with the experiment manager, we had to set up a parameterized model generation. To flexibly test various product mixes, we decided to program our own source. To achieve the wanted distribution with asymmetric upper and lower boundaries, we had to combine two normal distributions. To visualize the resource statistics on a network level, we had to combine the statistics of the individual machines in the background. To test our flexible production line concept, we had to implement special planning and material flow logics. To assess the various scenarios, we had to come up with a meaningful evaluation, and as we will see later, this helped also to find the bug. And given the complexity of the system and the many experiments to be carried out in limited time, special effort had to be made during programming to optimize the model performance. Now I will go into detail on two of them, but in case you want to know more about one of the other, feel free to contact me. Let's start with the custom product mix source. I'm sure you all know the standard source, but what is the essence of it? One section defines when to create something, and the other what to create. And there are various options how to do that, which are all based on MUs, which I call articles in this case. The one that comes closest to our need is percentage, that works with the share of different articles. But to use that, you need to be able to define that. And in our case, it would look like that. But with more than 1,000 articles and several scenarios to be tested, this approach was not feasible. Instead, we wanted to use a mix defined on process level. Having only 14 processes, this makes it much easier to make a forecast and define various scenarios. Since the standard source does not have such an option, we decided to make our own source with the following requirements. We wanted to create customer orders of a certain article and batch size. We want it to be easy to change the product mix and the total demand. And we want to have the possibility to apply a forced fluctuation on the target mix. In our routine, as shown here, we have the same basic sections as the standard source. So let's look at what to create first. For the routine to work, we had to introduce product categories, which are groups of articles with the same processes. Now, how does it work? It calculates the gap between the current and the target product mix, and it chooses the best suited category to reduce this gap. Then it selects an article of this category based on historical probability. And finally, it updates the current product mix with the selected article and batch size. Let's show an example. From the gap we can see that the article should have process 1 and 3, but not process 2. Therefore, category C is chosen. And from the various articles in that category, the most probable to be chosen is article 10. Now let's look at when to create. Basically, it defines when the routine will be called next. In this way, the total demand can be steered. To do that, first the average order sizes is calculated, and with that information, the time until the next order creation can be derived. I'd like to mention that this approach leads to a certain deviation between the simulated and the target demand, which reflects the real market. For this reason, several observations are required to obtain meaningful results. To conclude this topic, let's have a look how this source behaves. In the left plot, you can see the long time average share of 3 processes, one being always 100%. The dotted line is the target share that changes over time due to the forced weekly fluctuation. You can see how the actual share converges nicely to the defined target. The right plot shows the short-term average on a weekly basis. And here we can see well how the actual share tries to follow the fluctuating target over the entire time frame. Now let's move to the second challenge and the debugging journey. How to visualize and assess the performance of several observations and scenarios. Now if we look at this high-level process, intuitively one would simply compare the simulation output with the target demand of the source. However, due to the process and system dynamics, this won't give a meaningful result. Then an insufficient output does not necessarily mean insufficient production capacity, but it could also be that in that particular observation, the source generated less demand than defined. To create transparency on this issue, we came up with this input versus output plot. Every point represents the result of an observation, and as in this example, you can use it to plot production input versus production output, or depending on what you want to see, you can also plot ordered parts versus production output. So how to read this plot? These vertical and horizontal lines represent the target demand, so 8 millions in this example. And the diagonal represents input equal output, so all points below the diagonal mean an increase in inventory or backlog. Now comparing the results of these two scenarios, you can see that scenario 1, that uses less machines, does not have enough capacity to process the input. Scenario 2, on the other hand, performs well, because all points are along the diagonal. This means that it has a stable inventory. Only few observations had a slight increase in inventory, but they still reached the target demand represented by the horizontal line. So this plot really helped us to get transparency on the behavior of each observation and also about the statistical spread. And this plot can also help to make potential errors visible, as you can see in this example. This was the result when we first tested the simulation study with the experiment manager. Looking at this data pattern, it is rather obvious that there must be a bug. But without such visualization, this would probably not have been noticed. For instance, if we evaluated the scenarios only by comparing the respective averages of all observations. The first thing we did to find the bug was plotting the observations in sequence. And as you can see, something must have happened after 32 observations, because before all results are not plausible, and afterwards they are. So we started to think what could have happened during the experiment study. And in fact, we did not carry out the entire study at once, but in several sessions. 3 night sessions with 8 observations each during the week, and a long session of 32 observations over the weekend. We did that so that we could already work with the results during the week and gain first insights faster. But does this help now to find the bug? Not directly, but what stands out is the repeated presence of the number 8. So we concluded that the bug must have something to do with this number 8. And in fact, 8 is the number of logical cores that we used with the distributed simulation. As a side remark here, to be as fast as possible, we always used multiples of 8 for the number of observations. Now, for the 3 short sessions, this means that every core performed only one observation, and all of them were not plausible. And if we look at the long session, we can see that from the second observation onwards, they start to be plausible, which never happened in the short session because we only made 8. What happens during a distributed simulation is that every core opens an own instance of plant simulation. And it seems that the correct parameters only take effect after an additional reset and initialization. Therefore, we concluded that the bug must be in the initialization sequence. Let's look more in detail at the init call sequence of one observation. The correct sequence would be the following. At each new scenario, the experiment manager updates the experiment parameters in a central table, like machine quantities or the product mix. Since the model is quite complex, this information is transferred by an init method to different tables, variables, and attributes. These parameters are then used by other init methods to generate the model. Now, in our case, the model got generated before the new parameters got transferred. So our quick fix was to recall the init method that generates the model after the parameters got transferred. But 2 more elegant ways to fix it, or better say to avoid it, would be to either use standard methods and call them in a controlled sequence from a central init, or to control the sequence of various inits. And for that, please check out the Plant Simulation help under init methods and init controls to see how it can be done. To conclude this session, I will share with you my top 4 lessons learned. Number 1. Watch out with several inits. Whenever possible, use standard methods and call them from a central init in a controlled sequence. When various inits are required, control their call sequence as described in the Plant Simulation help. Number 2. Do enough experiment observations. As we have seen, too few could lead to wrong conclusions. I suggest to start with a high number and reduce it if the results are stable enough. But be careful to use averages without having checked the behavior of the individual observations. This brings me to number 3. Make things visible. This helps to detect mistakes and to avoid wrong interpretations. But start early with it. Implement the first diagrams already during modeling. And try different representations to find the one that gives you unbiased picture of the actual behavior. And last but not least, validate experiments with setups. This is just as important as the validation of the model itself. And I recommend to include this already from the beginning in the approach and the effort estimation. So, thank you for your attention. I hope you enjoyed my session, and I welcome you to contact me if you have any question or feedback.